All right, so now we're going to look at velocity time graphs. We have done the Buggy Lab and we looked at how to represent that motion as motion maps and also position time graphs. We have one more representation that we want to talk about. If you go back to the position time graphs worksheet, we had 4 different cars. We had car A, car B, car C, and car D. And in each one of those, we created a position time graph to represent that motion. And each one of those gave us a constant motion. So we had a constant velocity that was represented by the slope. So let's look at car A in a little bit more detail here. All right, now car A had a nice straight slope. It started at 0. It was a pretty basic motion, and we found out that it was in fact constant. So we go back to the motion map. This doesn't have the little cars on it, but remember the motion map has the dot at the position. So car A started at 0 meters. It started at the reference point. So we put a dot there. And then on the next tick, it was at 2 meters. So we put a dot there. And we drew a vector in between. And then the next tick was at 4 meters. So we put a dot. Next tick was at 6 meters, 8 meters, 10 meters. So at each position, we put a dot and then represented that as a vector with our motion map. Now in our position time graph, all right, so we had 5 seconds. And it actually went up by 2s, and so that was a pretty nice way to represent that. So at time 0, we were at 0 meters. 1 second later, we were at 2 meters. A second later, we were at 3 or 4 meters, wherever we were. And then at 3 seconds, we were at 6 meters. At 4 meters, we were at 4 seconds, we were at 8 meters. And 5 seconds, we were at 10 meters. Right? So that was the position time graph. That's how we got the position time graph for car A. And so now what we want to do is we want to put that onto a velocity time graph. So now remember that velocity is the slope of our line. And so we are going to have time on our x-axis, just like we do with our position time graph. But on our y-axis, we're going to have velocity. So the times line up. But what we're going to do is we're going to start with 0 there in the middle. So in this case, we're going to have a velocity time graph that has a positive and a negative section. So we're going to start with 0 there in the center at our reference point, and then we're going to have 1 meters per second and then 2 meters going up. And so then going down would be the negative side of our graph. So down we would have -1 and -2. So if we think about the position time graph, the slope of those graphs tells us the velocity. So if you go over to that position time graph and determine your slope, you're going to find that it's 2 meters per second. So for every second, our car is moving 2 meters. So to plot this onto our velocity time graph, we're just going to put a dot at 2 meters. Now we are going to assume, we are not going to assume that it was stopped at 0. Okay, so that's kind of a dangerous way of thinking. We don't always assume that at 0 time we have 0 velocity. So we could have had our car already in motion when we started the time, and we're going to assume that because we don't have any other evidence otherwise. So at time 0, our car was moving with a velocity of 2 meters per second. We're going to put a dot at 2 meters per second at 0 time. Now how fast is it moving after 1 second? This is a constant relationship. So at 1 second, we are also moving at 2 meters per second. How fast is it going at 2 seconds? It's still going 2 meters per second. So this is a constant relationship. So the whole time that we are measuring this, we have a velocity of 2 meters per second. So the velocity doesn't change. And we've talked about that, right? It's a constant relationship. The velocity is the same the entire time because the slope is a nice straight linear line. So that gives us a velocity time graph of 2 meters per second for the entire time. All right, pretty simple, right? Okay, now we're going to look at something really cool about these graphs. So in calculus, we have something called the integral. The integral is basically the area under the line of a graph. So for example, on this graph, if we take it and we kind of just draw a line, so let's just say between 1 second and 3 seconds, we can make a shape out of the line on our graph and the axis of our graph. And this shape is going to tell us something. Now, to find the area under this graph, what we're going to do is it's a square, right? And so if we look at the bottom is showing us 2 seconds of time. And the side is showing us 2 meters per second. Now, to find the area of a square, you take the width times the length. Now, what is our width and what is our length? The width of our square represents the velocity, and the length of our square represents the time. So what we're actually doing to find the area of this area under our graph is taking the velocity times the time. So that square represents the velocity times the time. Now, what does this mean? What does this tell us? So if you think about if you're traveling in a car and you're traveling for 100, oh no, that's going to go way too fast. Let's travel 60 miles per hour. We're going to travel 60 miles per hour for 1 hour. How far have you traveled? You've traveled 60 miles. What if you travel for 2 hours? You travel 120 miles. What if you travel for 5 hours? You've traveled for 300 miles. How are you finding out how far that you've traveled? You're multiplying your velocity times your time. So velocity times your time gives us what's called the displacement. It's our change in position. It's how far we've traveled. So that area under the curve of a velocity time graph tells us the displacement. In this case, it's a rectangle or a square. Okay. So the displacement between 1 and 3 seconds of our car is going to be the velocity times the time. Our velocity is a positive 2 meters per second, and our time is 2 seconds. So if we multiply those together, we get a displacement of 4 meters in the positive direction. Now, what if we go between 1 and 4 seconds? We can still do the same thing. This is still a rectangle. We can still find this area. So if we take this 3 seconds and this 2 meters per second, we can use the area of that shape to find the displacement. So we're going to take our velocity of positive 2 meters per second times our time of 3 seconds, and that's going to give us a displacement of positive 6 meters. So we can do this for any amount of the area under our curve. So what if we want to know the whole time between 1 and 5 seconds? All right, we're going to do the same thing. Displacement is velocity times time. We're going to take our positive 2 meters per second, and we're going to multiply it by 5 seconds. And that's going to give us a displacement of positive 10 meters.